here's an example. Now this is going to take us a while to get this all done. So the given table represents the winning distances for the men's discus event at the Olympics. Answer the following. Draw a scatter plot, and then it lists a whole bunch of things. So first of all, let's look at this table they're talking about. So we have years going from 1948 all the way up to the Olympics in 1996. And then these are the measurements of the distances. Now, just looking at the table, you can see that these distances are increasing. Are they increasing linearly? Not quite sure. So the first step they tell us to do is draw a scatter plot. Okay, so in order to do that, I need to know what my dependent and independent variables are. So what do I have no control over? It's going to happen whether I'm measuring something or not. Obviously, that's going to be the year. And we're going to see if there's a relationship with the distance. As the year increases, what happens to distance? So that's the first thing I'm going to do is I'm going to put year along my horizontal axis and distance along my vertical axis. Okay. The next thing I need to do is how do I mark things here? Okay, I'm going to go back and forth here. So I'm going from 1948 to 1996. Is there a distance here equal each time? Well, no, it's maybe there is. Let's take a look. From 1948 to 1956. So we're looking at how many years? Well, if we actually do the subtracting in between here, it does appear that it's going up by 8, even though the Olympics happens every 4 years. So that's the first thing I need to do. So what I would do then with that is for my horizontal distance, depending on what one I'm doing, I'm taking my highest number I have to go to, which is 1996, and subtract my lowest number, which is 1948. And we actually do that subtraction. What we end up is 48 years. So that means from here to here, I have to go up 48. Okay. Now, what we can do we want to start at 1948 here, or do we want to start somewhere else? Well, if we start somewhere else, what happens is we could predict what would happen before 1948. So sometimes we don't want to start right here in this case. In other cases, when we're talking about time and we're talking about 0 seconds, 5 seconds, 10 seconds, then I would want to start my horizontal axis at 0 for sure. Okay, so now we have to count. In most cases, we count the number of squares that we have and then divide it fairly evenly for the 48. And I just counted them, and there are 20 squares here. Now, if I do 48 divided by 20, obviously what I would get is I'm not going to get an even number. I'm going to get 2 point something. Now, because I want to draw this, do I want it to be a decimal? Probably not. So probably I would probably go up by, can I start here and go up by 8? If I go up by 8, am I going to be okay? Now the reason I'm saying going up by 8, because we know that everything from our table had a distance of 8. So we might be all right to do that. So we could go up by 8 because it is evenly spaced. So it's important for something to be evenly spaced. So I'm going to stop the video for a second. I'm going to evenly space mine, and then that's what you get to do. So what I've done here is every square is worth 4 years for me. So I've done 1940. So I've gone back 8 years. So every tick is 4. Okay, and so you see that I have everything evenly spaced. Okay, so not only evenly spaced, if I'm counting every 2, I'm putting a mark. It means that the distance between the numbers 1940 and 1948 is a distance of 8. Okay, so each square is a distance of 4. Okay, that's very, very important, whether we're talking math or science. Now I have to decide, by looking at the numbers, what my distance has to be on the vertical axis. Now, when we go back to our vertical axis, what we notice is I'm going from 52.78, okay, so 52 to almost 70. Okay, so again, I have to decide at what my scaling needs to be. So what I've done is I have shrunk mine a little bit so you can see, it's a little bit harder to see those numbers now, just so that you can see the whole graph. So again, I need to know how many squares I have in order to get my numbers to fit in there. Okay, so we're going to do subtracting again, counting our squares, and then dividing to see how we want to go up. All right, so I'm looking at, I want to start somewhere the numbers fit between 50 and 100. And I have 25 squares here. So what I'm thinking I'm going to do is each square is going to be worth 5. Now, for my y-axis, I want to make sure that I actually am starting at 0. The reason being is I know that I'm going to need to create an equation. And so it makes sense that in order to find my y-intercept, I want to start at 0. So each square is worth 5. Okay, and now what I need to do, so I have it from 0 all the way up to 90. I'm not sure whether a person's going to be able to throw it more than that. Okay, so that's what I've done with mine. So now what we're going to do is we're actually going to plot our data onto our axes. Okay, so I've brought the table over here just to make our life a little bit easier. So in 1948, it was 52.78, so almost 53. So here would be 55, so 53 would be approximately, it's almost 54, so somewhere in there. In 1956, it was 56.36, so this would be 55, so 56 would probably be approximately in here. Then in 1964, it was 61. Here's 60, 65, so 61 is approximately here. In 1972, it was 64.4, which is almost 65, so it's getting close to that line. And then in 1980, we had 66.64, which is almost 67, which there's approximately here. Okay, if you notice, we're estimating to a certain degree within our squares. 1988, it was 68.62, so almost 69, so getting closer to the 70. And then in 1996, it was approximately 69, so it's almost flatlined. Okay, so now we have our data plotted. Okay, so now let's see what they expect us to do next. Well, according to the question, it says draw a scatter plot, identify any outliers. So let's look at our graph. Do we have anything that is really outside of anything else? Now, I kept it zoomed pretty much so that we could see. Well, it kind of looks like it's going up like this. Maybe this one, but you know, it could be that maybe it's not linear. So let's assume it is linear. Maybe that one. There's nothing that sticks out in my mind that says, oh, it's really off. All right, so the next part, do we have any outliers? None. So we're going to put the word none there. And we'll just do it in no apparent ones. No apparent outliers. Describe the relationship between the x and y variables. Okay, so this is what we would do. So I'm looking back here. Well, it appears that as the year increases, so does the distance. Okay, so that's the first thing that I would put. So I would put that, I'm just going to make this a little bit smaller so I can fit more in. So I would say as x increases, y increases. And we'll say that it increases, it almost looks like it's linearly. Now, we know that in fact what would happen eventually over time is it would have to eventually slow down. It would, because human beings aren't going to be able to throw something unless something genetically happens to us that allows us to throw something a kilometer. I mean, that doesn't make any sense, right? Especially remember we're throwing discus, so those aren't going to change. So we're going to draw our line of best fit next. Okay, and so out comes my straight line, and I will keep it blacked, I think. And it appears that if I look at this, Have I done a good job? I don't think so. I think that it needs to be slanted a little bit more than what I have it, and maybe even up a little bit. So maybe something like that. So now if you look at the line of best fit, are there any outliers? Now I would say probably at year 1996, right? So now you can see that there is more of an outlier. So you could actually put that on your graph, that this is a possible outlier. Okay, so we've drawn our line of best fit. Next, let's see what they ask us to do. It says find an equation for the line of best fit. Okay, so now this relies on the information that we learned, hopefully we learned very well in our previous unit. Okay, so line of best fit. So what I need for line of best fit is I need y equals mx plus b. So y equals mx plus b. So that's what I need to look for. Okay, B is our y-intercept. So let's take a look. It appears to be right here, which is 50, 40, 49 maybe. So we're going to say B equals 49. I'm just going to change to black. So B equals approximately equal to 49, and that would be 49 meters. And then I need to find the slope. So I want to find where it intersects. Okay, so it appears that one happens here and maybe another. So I'm not looking at the green points. I'm looking at where my line intersects. So it appears that I am rising one square. Now remember, one square here isn't worth 1 anymore. It's worth 5. So that is actually 5. And if I look at my run, I'm running 3 squares, but each square is worth 4. Remember, we talked about that. So that would be 4, 8, 12. So my slope then is 5/12. And we leave it, remember, as a fraction. Okay, so I have my slope, I have my y-intercept, so therefore I know that my line of best fit is going to be y equals 5/12 x plus 49. Okay, so that's my line of best fit. Then they ask me to, using your graph, okay, so we're going to use our graph, interpolate the record for 1950. Okay, so let's look at this for 1950. So in 1950, here's 56, here's 44, so 1950 is here. So it would be approximately, according to my graph, it would be 50, 54, 53, we'll say 53. So for our graph, it would be 53. Okay, and remember that's 53 meters. Then we're going to interpolate for 60, well, using a graph, interpolate when the record was 62.9. Okay, so this time I'm going to 62.9. So I find roughly 62 on here, and I go directly across, and using this, I know that's not a straight line. So that would happen when I go straight down in the year. Okay, this would be 1968. So maybe 69, 1969. And then it says, using your equation, extrapolate the record distance for the 2008 Olympics. And then also using our equation, they also want us to find the record in 1975. So I'm going to stop the video for there, and we're going to actually look at our equation for that next.